corrections for me? Oh, yes, of course you do. Yeah. We've got homework and notes for you. Okay. Excellent. Just leave that in the middle of the table for now. Oh, golly. Love teaching good-looking kids. It's the ugly ones I don't like. All right, Victoria's here. I'm going to pretend she's not trying to sneak in and go to her locker because I'm so focused on you all, right? She's not going to her locker right now. We already had that conversation. And Abel didn't show up late? No, of course not. All right, so while you're checking your homework, you are going to see that I was finding derivatives the painful way. OMG.
Like pain.
I apparently like pain because in my differentiability notes, when I worked through the solutions, I was only using this formula all the time. It's like I didn't know my power rule stuff. So I hope some of you, when you were doing the differentiability, were able to say, oh, no. I know how to find the derivative of 1 over x. And you use negative 1 over x squared. If not, you went this way, route. Hopefully for 2x squared minus 5x plus 4, that was one of those that you just know on sight now that the derivative is 4x minus 5. And this one was maybe a little bit tricky, but it's also a power rule if you think 6x to the half. So no, I went the painful way, but you could have gone the shorter way. You got 3 minutes, make the most of it. I care greatly about the notation. Irene, Fabrizio. Feel free to write all over this assignment. You're giving yourself feedback. Jasmine, here you go. Juan, my hand started shaking this morning when I ate my banana after my walk. Thanks.
Did you eat more than half?
I did. Three. I walked in the car. Oh, bring it. Yeah. Check in the homework.
Don't you ever heard that word?
No. Claudia.
You're Mexican.
Okay. 3, 7, 11, 14, 16, 19. Jaylene.
Your Mex. Your eggs.
You say you're
No.
Oh, yes. I got everything right.
How'd it go?
For today, tonight is C, D, E.
No. How'd it go?
I got negative.
Because I was doing this.
It's not that f prime is not differentiable. F is not differentiable. Just leave it over there.
I did.
Is this on already or not yet?
It is.
On?
Alrighty.
When I say calculus, you say ready. Calculus.
See, you have no power here.
Ready?
A, B,
Yeah.
1 or no?
Negative 1.
Okay.
Negative 1. Okay.
In the piece.
Alrighty, please put that in the middle of the table. My lunch group, I am going to go through and grade the whole thing from start to finish like I did the free response on the unit test. We had that conversation yesterday. This is not new information. For everybody else, the feedback that you're going to get is the feedback you just gave yourself. Okay? So let's put the homework in the middle of the table. While that's happening, I almost forgot the most important thing that is happening today. There is nothing more important than the fact that it is Salma's birthday. Woo! So, 18 today? 18 years old. You are a woman. a woman in the calculus class. So on the count of 3, let's do it in style. 1, 2, 3.
Happy birthday to you.
Cha cha cha.
Happy birthday to you. Happy birthday, dear Salma. Happy birthday to you.
Wow, we just took Yes, it's also awkward, honey, to clap for yourself. Okay. Janaea, go do your thing. Josue, I need you to take control. Cynthia, you've got the camera going. All right. So, today, the goal, we are starting to make deeper connections between f and its derivative graph. I want to throw the doors wide open on your brains. I just want you to look and see and feel and explore. We're going to get to sketch. You're going to get to color. For those of you that like the colors, pull out the markers. You are ready. Okay.
How many colors are there?
2 colors is probably going to be good enough. And Josue, click the button where it says hide XF double prime. Hide XF double prime. All right. So I am not going to tell you lots of stuff. Today you guys are going to tell me lots of stuff. I'm looking for strong vocabulary. Know that when we are talking about the function, if you use the word it, I will get very, very angry. Cynthia, is the camera going? Excellent. Okay. So 30 seconds, turn to somebody near you. Tell them all the things you know about this graph that's in front of you. All the things. All the vocab you know, get it out of your system.
Right there.
Closing out in 5, 4, 3, 2, and 1. I want to hear from 8 different people. I'll take anything from anyone, stuff you know. Birthday girl, start it off.
It's differentiable.
I'm sorry, what?
The function is differentiable.
F is differentiable. I was not expecting that so soon. I love it. F is differentiable, not Selma. Somebody tell me. Alex, how do you know it's differentiable?
Doesn't it have a vertical line?
Wait. If the function's differentiable, there's 3 things. One cop, what are we looking for?
Function is continuous.
Is this function continuous?
Yes.
Everywhere, right? What else?
There's no cusp.
There's no cusp point. Make that cusp point for me. There's no cusp point in the third thing. Third thing. Josue.
There's no vertical tangent line.
Great, because all those things are true. This function is differentiable where?
Everywhere.
Everywhere. It's smooth. Like iron smooth. Not to be confused with round. That's different. Okay, give me something else.
No, I was confused.
Okay, stay with me. Other things about this graph. Other things. Other vocab words you would use. One go.
It increases.
What?
The function increases.
The function increases where?
From 1 to 2.
From like 1 to like over here?
Yeah.
Right, these are the things I really want to make sure you're adding onto the graph. This function is increasing, starting at 1, going on forever. Great, what else? What else? Other things. Shunli.
I'm not sure, but it looks like it stays constant.
It looks like it stays constant. The graph looks like it stays constant?
Like
Where?
from the point, like around the 1 point.
Around x equals 1, we kind of like flatten out. I think part of it is you guys don't actually have a vocab word for this yet. So the word is, first of all, is everybody okay? We kind of see it like we're increasing, we flatten out, and we increase some more. The word is saddle point. S-A-D-D-L-E-P-O-I-N-T, saddle point. Like a saddle you would put on a horse. There is a saddle point there. Other things. Other things. If you've already shared, you're frozen. Other things you notice about this graph. I'll take anything. It doesn't even have to be calculus. Things that you know. Just don't tell me it's blue. Miguel.
It decreases from negative infinity to 0.
Oh my God, the word it again.
F of x decreases.
Thank you. F of x is doing what?
Decreasing from negative infinity to 0.
Just got it.
Good. Okay. What else? What else? Other things you see about this graph? Brianna.
There's a point at 0, 0.
There's a point at 0, 0, and I know there's some fancy vocab words we could throw out here. It's okay. It's the origin. Yes, the graph is passing through the origin. Something else that's so special? I don't want to use the word vertex. Here's why. Here's why. Vertex is for a parabola. Vertex is for a parabola. This ain't no parabola. Okay? But there is another word you could use here. It begins with an R.
Root.
It's a root. You have a root over here. Okay? You could also describe this as a... You could say it's a root, you could say it's a 0, but there's also something happening here. That graph is turning, right? The graph is changing from decreasing to increasing. You guys would call this a...
Double root.
Not a, it is a double root because we're bouncing. True. What I was hoping to get into your brains and out of your mouths.
Oh, is it upward? Upward.
No. Okay.
Opening.
Now you're talking about concavity, which is good. The other thing I was hoping to hear, and it didn't come out yet, is that you have a relative minimum. You guys know that word, right?
Yeah.
Okay, last class had some confusion. They were telling me that this graph was an even function. Was anybody thinking even? You're not even sure what that means. Even functions have y-axis symmetry. Even function, you can take out your samurai sword, cut it down the y-axis, and what you see on the left and what you see on the right are equal to each other. Do we have that?
No.
No. But there is something having to do with even that you learned last year with Mr. S. I swear, I was in the room when it happened. It had to do with the tails. Those ends. Juan Kyle, what is it?
They're both going up.
They're both going up, so there's something. What do you know?
The end behavior is, I don't know if it's like, it's even, it's the same in both ways.
The degree is even. Which is not the same as saying an even function. Even function means symmetry. Even degree is telling you about the tails and how they behave. All right, so now we're going to ooh and ah a little bit. Josue, you ready? We're going to start looking at the derivative graph. So first of all, show me xp tan sec. Okay, no surprise here. We've seen this before, right? That point P, fancy word?
Secant.
Not a secant.
P.
P
Point.
is the point of tangency. The black line? I heard somebody say secant. That was probably just a mistake, right? We get a little too excited. Okay, we're touching the graph one time, so tangent line. Good. All right. The information that we're seeing over here, the blue says that at 0.614, the y value is 0.836. The green says the slope is 1.099. Everybody get the lay of the land? All right. We're going to ooh and ah. Josue, slide x, please. Oh, wait. Whoa. Hide xf prime. Oh, okay. Dude, you're going rogue. Hide xf prime. Now slide x. Ooh.
Party. Ooh, wow.
Josue, let it keep going. Okay. So I want to introduce you guys to another thing. Show xf prime. Now there's a green dot. Let your smarticle particles do their thing. I'm going to talk more about the green dot in a little bit, but I want to give you a chance to see if you can figure out what's happening with the green dot. Okay, Josue, next time the green dot shows up on the screen, hit slide X so it stops. Anybody think you know the significance of the green dot? What's going on with the green dot, Janaea?
Isn't that like the opposite of the
Okay, you're thinking it's the opposite. Selma, what are you seeing?
The derivative.
Okay, the green dot definitely has something to do with the derivative, and the notation tells us it has something to do with the derivative. Miguel, you thought you saw something?
I was gonna hallucinate.
You're seeing some sort of opposite behavior happening? Yes, Jasmine.
It means it is differentiable?
Well, we already knew that the graph was differentiable because the graph was continuous, no cusp, no vertical tangent line.
Wait, that's not, I was confused. You didn't let me talk.
Okay, I'm going to do it to you a second time. What about it? All right, let me tell you about the green point. The green point is following the point of tangency. The coordinates, and you might want to jot this down in your notes somewhere. The coordinates for the green point, you need to know where the x value comes from and where the y value comes from. The x coordinate is the same as the x coordinate from the point of tangency. We're okay? The x values are always going to be the same, which is why they're moving together. The y coordinate is the slope of the tangent line. So let me say that again. The y coordinate is the slope of the tangent line. I missed you yesterday. All right, so with that in mind, let the green point do its thing. I'll sweat.
You said
Brianna, what was your question?
you said the y value was the slowest or the slowest?
No, the slope of the tangent line at point P. So watch the green point. That green point moves. It moves really fast, but it moves in a very deliberate, very predictable way. The x coordinate is the same as the x coordinate from the point of tangency. The y coordinate, how do we get the y coordinate?
The slope of the tangent line.
It's the slope of the tangent line. Okay, so when the blue point is over here on the blue graph, where's the green point going to be? We're going to be below the x-axis. Abel, how do you know that?
Because since the function is decreasing, that means
Love it. Function's decreasing.
that means that the slope of the tangent line is going to be negative.
Slope of the tangent line is going to be negative. That puts the green point down here. Are we good? Okay, where's the green point going to be over here?
Up there. Like
It's going to be up above, right? Okay. Green point when you're over here? Cassandra, where's it going to be? It's going to be awkward? What? It's going to be up, but look right here at 0. What do you know about the slope of the tangent line now? The slope of the tangent line at this minimum, there's something that everybody needs to know. What is the slope of the tangent line right there?
Positive.
It's not positive.
0 constant.
It's 0. It's not, don't say constant when you mean 0. The tangent line is horizontal here. You have a horizontal tangent. I think I would add that onto the graph. You have a horizontal tangent line here, and you have a horizontal tangent line one more place.
Stable.
Oh,
Saddle.
At the saddle point, you have a horizontal tangent line in the stable. Golly, take tomorrow off too. Okay. All right, Josue, we're just going to let this go for a few more seconds. And what I want to do is I want to show you the graph of f prime. Graph of f prime. Click show f prime. Nope. Just show f prime. Wait. Okay. Show f prime. It's the one that says show f prime.
The other one.
There you go. And let's hide f. There we go. Good. Somebody asked me the other day. They watched the video. They're like, "You have a smart board at Southwest?" I'm like, "No, I'm giving directions to my smart board." All right.
Oh my God. Smart board.
Smart board. Okay. Look at the green graph. Why does the green graph look that way? Have that conversation with somebody near you. Why does the green graph look that way? Oh my God, I heard 4 people just use the word it.
The function is decreasing at this.
The green graph is the derivative graph, Shanley.
Are going to be negative. And that's why it's under, and then it comes up. And then the function
All right, Josue, if you could go back and hit the slide X button. Okay,
we can't say it's opposite.
slide X. Okay, how many roots does the green graph have? How many roots? 2. Where are they? And over here at x equals 0 and right over here at x equals 1. The green graph, this is important information for you to capture. The green graph, the derivative graph, has roots when what happens with the original? Alejandro.
When the original is at 0.
You said 0 when you did this. When you have the word I'd love to hear is horizontal tangent line. If the blue graph, the original function, has a horizontal tangent line, then the green graph has a root. Because the green graph is telling you about derivative stuff. When the blue graph, when the original function is decreasing, the green graph? Not decreasing. If the blue graph, the original function, is decreasing, think about slope.
Negative slope.
The slope here is negative, so the green graph is below the x-axis. Over here, I see my function is increasing. Somebody describe the function as increasing over here. The blue function's increasing. The green graph is not increasing. If the blue graph is increasing, the green graph, the one thing you can say for sure, if the blue graph is increasing, you know slope stuff. If the function is increasing, the slope is positive. You can't tell me for sure that the green graph is increasing or decreasing, but it is true that whenever the blue graph is increasing, the green graph is positive. It's above the x-axis. Increasing again, derivative is positive. Okay, now we've got a couple of minutes here, so I want to go for extra innings here. Don't worry about getting this copied down. Just ooh and ah, Josue. Smartboard. Show x f double prime. Slide x. Here comes a pink point. It moves even faster. F double prime. We all know what this is. F double prime, what is it? It's f prime prime. It's the derivative of the derivative. So, if the blue is the original function and the green is the derivative and the pink is the derivative of the derivative, where's the pink point going to be when I'm right here? At this point right here, the relative max for the green graph, isn't it going to have to be at 0? Because the green graph, the derivative has a horizontal tangent line. Okay, show me the f double prime. And let's hit slide x so it stops sliding. So you've got your blue graph, which is the original function, the green graph is the derivative, and the pink graph is the second derivative. Everybody mostly okay? Miguel.
Will there ever be, like, can you find infinite derivatives?
I can. I have a master's degree. I can go forever. Yeah, and we can even go backwards in the derivative process, which is called the antiderivative. I can't wait. All the stuff that's coming. All right, Josue, I want you to go over to model number 2. Everybody else, I think you're on page 2. And I promise I'm going to answer your question about differentiability because I know you don't like that I've ignored you twice. All right, Josue. Wow, Josue's taking some control back there. He really is getting to be a smart board. All right, hide xf prime. Hide f prime. Okay. Same conversation from before. What are all the things you know about this graph? Get it out. The original function. Things you know about the original function.
X to the power of x.
Oh, you're right. No, I don't know. But wait, but still, there's
Is it this 10? Yeah, I guess 10. What's it go 10? Oh yeah, it is. What is it just like continue?
All right. So here are things that I heard. I heard that this graph is continuous. Do we agree?
Yes.
I heard that this graph is increasing. Okay. I heard that this graph is the graph of y equals x cubed. I disagree.
No.
Cube root.
It is. Okay. It kind of behaves like the arctangent function does. I know, like when I put something into your brains, it stays. Everyone's like, it's arctan. I was ready for this. It's not the arctan. This is the graph of f of x equals the cube root of x, which looks a lot like the arctangent graph does. There is a reason, though, I wanted to look at this. There's something special happening here. Wanka, what do you see?
Vertical asymptote.
Vertical asymptote? No, there's not a vertical asymptote.
Vertical.
What did you mean?
Vertical. Horizontal.
Don't. Vertical, you're right. There's one other vertical thing, Wanka. It begins with a T. It ends in angent. Vertical tangent, yes. I worked really hard here. The graph has a vertical tangent. I know, Miguel, you were not here with us yesterday when we came to this idea of vertical tangent. So the graph is differentiable there?
No.
Not differentiable. Not differentiable. Good. All right, so let's do it. Let's slide X. Let's show XF prime. Watch that green dot. Watch that green dot. It moves a little bit slower. It's a little easier on the eyes this time. Is the green dot behaving the way you think it should?
No.
Well, somewhat.
Somewhat. So I'm hearing some yeses, I'm hearing some nos. I want to hear from the folks that are saying, yes, it is behaving the right way. What are some of the things that you see? Juan, what do you say?
I think it does behave, the function does behave as like we would think, because like at that point,
What point?
whenever it's like crossing the origin,
Yeah.
it goes like straight up and then it goes down.
The green point goes straight up and then it comes back down. Okay, what else? Shunli.
I thought it wasn't
Okay, tell me what.
because the graph is always increasing.
The blue graph is always increasing. The original function is always increasing. So what do you expect is going to happen with the derivative?
That it's gonna keep going up and it goes down with the derivative, like on the side.
Okay. So I want to help you out with that. The blue graph is always increasing. Are we okay with that? If the blue graph is always increasing, the one thing that is true about the green graph,
Slope positive.
if the original function is always increasing, the green graph is always positive. It's always above the x-axis. Okay. Add a vertical tangent line, we're going to have some problems. Salma, what else?
I don't know if I'm seeing this right, but isn't it disappearing like up there, like a little past 3?
So let's see what happens. Show me the graph. Show me that beautiful graph. So there's the green graph. The green graph is always above the x-axis. Hopefully no surprises there. What's happening on the blue graph right here at the vertical tangent line? Imagine your tangent line. The slope here is going to be, well, the slope is positive. Over here it's more positive, right? More positive, more positive, more positive. That's what the green graph is doing. As I get closer, I'm more positive, more positive, more positive, more positive. But when I get a vertical tangent line, that derivative doesn't exist because slope of a vertical line does not exist. It's undefined. It's been undefined forever. I'm going positive, 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 more positive. Green graph increasing, increasing, increasing. Undefined over here at x equals 0. Even better, you could say that what you have is a vertical asymptote. You have a vertical asymptote at x equals 0. That's for f prime. Now, last class, some folks noticed that the green graph seems to be decreasing, right? It's getting closer and closer and closer to that x-axis. And some folks were like, is that a horizontal asymptote?
No.
Actually, it is. Because the blue graph, as you go out further to the right, that tangent line still has positive slope, right? But it starts to flatten out. It gets less and less and less and less and less positive. So what happens is the green graph gets smaller and smaller and smaller and smaller and smaller, positive. Okay? Right now I'm planting ideas. They're going to grow. All right, we got 2 minutes left, just enough time. Go to the last page. There is another graph here that what I want you to do is I want you on your own to sketch what you believe the derivative graph would look like. Josue, if you could hit the slide X so that it stops sliding, and then click on the CFU button and get rid of the green graph. There you go. So we've got the blue graph. Give me a quick sketch. What are the things you know for sure about that green graph? Usually when I'm sketching these, things that are easy for me to get on the first derivative, I look for where the root's going to be. You guys show me on your fingers, how many roots are you expecting f prime to have? I'm seeing 1, I'm seeing 2, I'm seeing 3. Remember, if your function has a horizontal tangent line, then your derivative is going to have a root. So you have horizontal tangent lines at both of those places, your derivative is going to have roots. Horizontal. Right, that's what a horizontal tangent line is. All right. This way we're going to ruin all the fun for everybody. Show f prime. Hopefully your graph looks something like that. It doesn't have to be perfect. These are sketches. The things that I care greatly about, when your graph of f has a horizontal tangent line, do you have a root?
Yes.
Okay. I care greatly over here for you to say, oh, well, the blue graph is, what's that blue graph doing? The blue graph is decreasing. So the green graph is below the x-axis. It's negative. Over here, my blue graph is increasing. My green graph is positive. These are the things that I care about. Tonight's homework is this. If you look on the last page, round 1 is just practice with derivative rules. Round 2, more practice with differentiability. We're going to get better because you're going to get the practice. Tomorrow, we've got a whole lot of folks from North Central who are going to come and join us. So, you know, make sure you're like looking good, ready to represent.